Posted it up here at the top of the Moodle area, just underneath our pictures. Okay, so here's some copies of it. Get out. Everybody here today? 6, 9, 2 people missing.
Going well.
Okay, so it's in the form of a report. We want you to submit solutions to these. We recommend typesetting the report, but it's not a requirement of it. But I think that's the best way to go about it, for drafting and redrafting your work. But we don't mind handwritten solutions either. And you can get full marks with handwritten solutions. Submission date is Friday, the 18th of January. I guess you're used to submitting stuff. It's 40% of the unit. There's indications of the part. Well, there's 4 questions and they're 25 marks each, I believe. And we're going to mark it according to how well you present correct treatments of the questions. We want your reasoning clearly explained and justified, and accompanied by reference back to relevant concepts and results from the textbook and from the unit. Please attempt all questions. Marks are available for partial progress through the questions as well. Okay. Some of the questions ask you to include a bit of work with Sage, and so you should, depending on the question as appropriate, include a printout or some kind of nice export of the worksheets showing the code you've used and the output or samples of the output and that. Read each question carefully and follow the guidelines. And we'll endeavour to have it marked and returned to you in the usual period. And, well, I think we're pretty accessible to you. So we've got office hours there, but I think you can find us without too much trouble. So we come to the questions. Some of them are based off, in fact, most of them are based off actual exercises from Judson's book. And Jan, the first one kind of belongs to Jan, so I'll let him take over and say a few words about the first one. Sure. I'll have a sweet.
Yeah, I think it's obvious.
You might think that now.
I mean, the questions are. I don't mean the solution is obvious. The questions are kind of self-explanatory.
So this is some text about what DN is and what AN is, maybe. But you know that from the lectures, what the alternating group is, the permutations. The question asks you to say for which n it's abelian, so any 2 elements commute, and for which n it's not. So the answer should look like, I don't know, it's abelian for n equal, when n is a prime, and it's non-abelian, and not a prime. An example, it's wrong.
But that's not the right answer.
It's not the right answer, but that's an example of an answer.
Yeah.
And then the justification would be, well, suppose that n is a prime, and then you prove that it's abelian, or whatever. Similar for B, it's the same thing. The dihedral group, so you have the regular n-gon and all the rotations and reflections and all that. That forms a group, which we talked about in the lecture. So again, this asks for which n is abelian. If it's abelian, then you have to prove that any 2 elements commute. So if you do xy, it's the same as yx for any x and y. If they don't commute, it's non-abelian, And of course, it's enough to find two specific elements, and show that if you do them in one order, you get a different result than doing them in the other order. That's how you prove that something is non-abelian. And the third question introduces the center of a group, which we'll talk about later again, but for now, the center of a group consists of all the elements of that group which commute with everything in the group. Okay, so for example, the identity, whether you multiply x with the identity from the left or from the right, you always get the same answer, no matter what x is. There could be some other elements in a group, which, whether you multiply from the left or from the right, you always get the same answer. So later we'll show that this is a subgroup, but you don't have to show that it's a subgroup. What you just have to do is find the center of the n. So this is a bit of a thinking or investigating question. How would I approach it? Well, I would probably look at what is D3. So what is the center of D3? Try low values of n. What is the center of D4? And I find it, and then when I think I know the answer for all n, I try to produce a bit of proof. So this is the hardest bit. A and B should be more or less fine. I don't think Killian said it, but the number of marks awarded does not necessarily correspond to the amount of work. Okay, so you might have a question. This is kind of a warm-up question, probably the easiest of the four, but it still gets the same amount of marks as all the other questions. So it's kind of like everybody gets something done and nobody will fail. So, yeah. And then the people who do everything, they will get very good marks. Yeah.
And so when you say at the top that some of the questions are taken from what we've got, obviously they don't really taken in the exact same, or does that just mean that some of them are based off a similar topic?
Yeah. Some of them are very similar to the. Yeah.
Go a bit up, please.
And then you know where to look for the relevant material.
So it actually gives you these three exercises were exercises in the book in section 5.3, questions 18, 19, and 29.
I feel like C was one of the homework.
C was one of my homework questions, but nobody bothered, so nobody gets any answer.
I tried, I couldn't do it.
Oh. Okay. So question 2 is kind of from me. And here we're looking at the dihedral groups. So the dihedral groups, you reminded what they are in the introduction to question 1. So that, that serves as an introduction to question 2 as well. So cast your minds back to chapter 6. We proved Lagrange's theorem. It's a very important theorem in beginning group theory. For a finite group G, Lagrange's theorem limits the possibilities for subgroups of G, right? Any subgroup that a finite group has, the size of the subgroup has to be a factor of the size of the group, okay? So it means the subgroups can only possibly have certain sizes, okay? So it restricts the possibilities for subgroups. What this question is about is a conjecture or a question in the opposite direction. If you're looking at a finite group and you're looking at a divisor D of the order, there's the question: does G have a subgroup of that size? Okay. A group. So this is the definition of the term. So a group is termed Lagrangian if it has a rich set of subgroups. Meaning precisely that for every divisor D, the size of G, it has at least one subgroup of size D. Okay? In short, this question is about proving that the dihedral groups are Lagrangian. Okay. Now, in part A, you're asked to give a thorough description of all of the subgroups of Dn. And to do this for every n. Okay? Your description should detail the elements of each subgroup, provide enough explanation or justification that they are subgroups, and enough explanation and justification that your list is complete, that you haven't missed out any subgroups. Okay, so I should be able to come along to your work with an n in mind, like n equals 100, and I should be able to read off effectively, or I should be able to obtain precise descriptions from your work for how many subgroups D100 has, what do they look like, what sizes are they, what elements are in them. So you need some kind of a formulaic description of the subgroups of Dn. Then part B, you should have enough in part A then to give a proof that the dihedral groups are Lagrangian. Each dihedral group satisfies this. It has at least one subgroup for every divisor D of the size of Dn. Yes?
Should it be n strictly greater than 2?
Yeah, well, if you take the geometric definition of a dihedral group, then yeah, the geometric definition is symmetries of the polygon. That only makes sense from n equals 3 upwards, right? Yeah, you're right. But you can actually, the definition given in here as a group presentation, a group that's generated by elements R and S with these kind of relations, that is valid, that holds valid for n equals 2 as well. So sometimes people speak of the dihedral group D2 because they're talking about it as defined as generated by two elements, R and S. R squared is the identity, S squared is the identity, and they commute like this. Okay, but don't worry too much about that. If you begin at n equals 3 for all the n, I think that'd be fine as well. But then D2 will be quite easy to analyze because there's only like a small number of elements in it, 4 elements in it. So, yeah, 4 elements in it. Not particularly. No. It may do, but I haven't included it. But not particularly. In part C, make use of SAGE. So SAGE has subgroups methods and an order method, which you can. So if you have the name of a group here before this, if you define a group G in SAGE and do G.subgroups, you get a list of all the subgroups of G. And if you call G.order, you get the size of G, or subgroup.order, you get the size of the subgroup. So I want you to use that. Just show me a few for loops that test a bunch of dihedral groups and show that they have, because you'll be able to, SAGE will tell you what all the subgroups are. You'll be able to loop through them, ask for their sizes, and just confirm that what the work you've given, the listing you've given in part A agrees with what you find from a little bit of experimentation with SAGE. So you're validating your work from part A. And then finally, which of the subgroups are normal in Dn? Now we haven't treated normal subgroups will be dealt with by Jan from next week. Okay, normal subgroups in the quotient. Factor group. So that's question 2. Question 3 passes to Jan again. Funny question.
Okay, so does everybody know what the tetrahedron is? You have 4 equilateral triangles in space.
So you can build it.
If you take 6 skewers or something, you can build a model or from paper.
And then there are some things that you can do with. So rotational symmetry means. So rotational symmetry means that's all the things that you can do with the paper tetrahedron, just moving it around when it ends up in the same, taking up the same space, but maybe a different position. So, for example, if I number the vertices 1, 2, 3, 4, and each of the, it's not very good.
Do you want a better one? Am I distracting you?
No, but so if you have 4 vertices, right? So for example, this is 1, and then this is 2, 3, 4. So you can keep the 1 in place and rotate this triangle so that 2 goes to 3, 3 goes to 4, 4 goes to 2, and then you rotate it again. So these are rotational symmetries, but there are other ones where you can fix another vertex, and there are other ones, and I'm not going to tell you what they are because that's your job to find out. So all these things where you symmetry. Question 8 says describe the group, which more or less what it wants is just to describe it in the words I've used. So like you fix one vertex and you can rotate the triangle, and then there are other elements which look. So you just kind of list the elements. That's a good answer to question 8. So you can. Question B tells you that if you use an appropriate labeling of parts of the tetrahedron, for example, the vertices are 1, 2, 3, 4, which is the current darkness at this time. You can describe it as not what happens to the whole tetrahedron, but only what happens to the vertices. So you can have a set. One of them was 1 stays in place, and 2, 3, 4 form a cycle. 2 goes to 3, 3 goes to 4, 4 goes back to 2. Okay, so that's an example of an element of that group. So when you list them all in this notation, 1, 2, 3, 4, as permutations, you will get a group of permutations, and it so happens that it's the alternating group of 4 elements. So your task is to somehow argue, probably by listing them all, this is what this does. Making sense? I feel like not too much. Anyway, so yeah, so now you have the A4. That's kind of the introduction, and then what you want to do here is find all the subgroups of A4. The exercise suggests that you should use SAGE and look for orders of elements and generators and so on. And I want a full list of all the subgroups of A4 described in a suitable way. Yeah.
That makes sense.
For example, there's still the same example where you fix vertex 1 and you only rotate one triangle. That's a subgroup because it's closed in the position. You always only rotate the triangle. That's an example. Okay. If you can do it without using SAGE whatsoever, I think that's also fine. So it's open to SAGE. But if you don't use SAGE at all, and what it actually does not want you to do is to justify that this is all the subgroups by just using the subgroups command. Okay? So you can use it so that you know what they are, but then the argument that that's all of them should be independent of what SAGE told you they are.
Use it as a way to validate your work and look ahead to the right answer, but you need a justification of it without appealing to the subgroups then. Yeah.
And the last bit is the same as what it was in question 2. For each of them, you should say whether it's normal or not, but you don't know what normal is, but you're going to know what normal is next week. I think that's everything enough.
Yep. And question 4. Yeah, maybe fun. So this question is a really nice result. It's quite a decent, substantial result. It's classifying all groups of order 2p, where p is any prime number, odd prime number. Okay. So in this argument, you're going to reach a classification of all groups of order 6, all groups of order 10, all groups of order 14, 22, etc. So any group of size 2 times a prime, you're going to classify. Now, for any p, the answer is that there's only 2 groups of order 2p. One is the cyclic group of order 2p, namely Z2p, the integers mod 2p under addition mod 2p. It's a cyclic group generated by 1, it's got size 2p. The other possibility is the dihedral group dp, symmetries of a p-sided regular polygon. Okay? So, and that's all there is. Any group of size 2p is isomorphic to one of those two. It's either a cyclic group of size 2p or it's, in effect, the dihedral group dp. It's isomorphic to that. Now, what you have here in parts A to H is like is the skeleton of that proof. So this is a series of intermediate results and instructions for how to prove this classification result. Okay, so it's to guide you through the argument. So what you'll be doing here, you should be working to prove each one in turn and present the final complete argument in your solution, using references to results from the textbook as appropriate. Some of these steps are easy, some of them are harder. And for some of them, I've given extra hints as well. Okay? The very first, so at the start, you're assuming G is a group of size 2p, or p is not prime. The first step you have to do is argue that for any element A and G, it must have order 1, 2p, or 2p. Very significant result we studied in the last few weeks that tells you why must an element of G have order one of these 4 possibilities. And from there, these various steps guide you through the various intermediate results you have to get to in order to be able to prove this. So remember, there's credit available for partial progress. So you don't necessarily, if you, for instance, get stuck on part D, but you're able to move on, and assuming part D, you're able to give good arguments for the other ones, then that's, you should work that up and have, don't feel bad about submitting that. There'll be partial credit available to you, even though you've skipped out one of the steps or assumed one of the steps and so on. Yes, question.
So it is set up in a way that you could technically leave out one, like you leave out C and still be able to answer the rest of them.
So you could answer the rest of them, assuming the result of part C. Okay. And don't try and size, you won't be able to slip it past me, but I'll read it. Yeah. If you get stuck, So if you get stuck on C, for instance, move on and try and build arguments for the other parts using the result of C, and then you can come back later and work on that some more and try and solve that. So there's plenty of guidance there. Like a much tougher result would be, provide the argument that every group of 2p is isomorphic to one of those options. But here it kind of guides you through the argument. Yep. So any further questions? Okay. So there's a mix of stuff there. As Jan said, the first question is kind of introductory. Get the ball rolling. Get some marks under your belt. Questions 2 and 3 have similarities in them. You're tackling a certain class of groups, describing the group. Well, in 2, you're tackling a class of groups, describing it, describing the subgroups. In 3, you're tackling a particular group, symmetries of the tetrahedron, rotational symmetries, and examining that in detail, its subgroups in detail, answering this normality question, which you'll understand from next week. And then the last one, this nice classification result. But I really like this last question because it builds to quite a substantial result. It's a very strong result. The groups of size 202, 2 times 101, 101 is prime. The groups of size 202, although that's like 202 elements, there's, you'd imagine there'd be loads of groups of that size. Well, it turns out there's really only 2. Cyclic group of size 202 and the dihedral group D101, symmetries of a 101 God. Okay? So there ends the introduction to